Direct rendering of clean transparent surfaces is well studied in computer graphics. However, transparent objects in the real world almost always have surface contaminants, such as dust, dirt, and lipids, which can generate many interesting visual effects. For example, the dirt on the window looks darker against the sky, while it looks brighter against the ground. The stains on the wine glass create an interesting soiled appearance. Dust on a camera lens generates lens glare and a washed-out effect in the image. Fingerprints and other contaminants are visible on a monitor when it is off, while they are almost invisible when the monitor is on. All these effects greatly enhance the perception of transparent objects and can be used in realistic image synthesis and game development. In this paper, we take a significant step toward modeling, measuring, and rendering contamination on transparent surfaces. For a clean transparent surface, Snell's law and Fresnel equations can be used to determine the reflected and transmitted light. If the surface is covered with a contaminant layer, part of the incident light will go through the contaminant and be mirror reflected and transmitted as before. The rest of the incident light will scatter inside the contaminant layer and finally be reflected back or transmitted into the surface. In many cases, the contaminant layer is optically very thin, so we assume single scattering dominates and aggregate the light transport as a local BRDF-BTDF model. As expected, both the BRDF and the BTDF have two components. One is the specular reflection and transmission attenuated by the contaminant. The other is the diffuse lobe generated by the scattering. Here we show how the corresponding components change as the optical thickness tau increases. We also show these components with respect to the incident angle. To measure the thickness patterns tau xy, we use a projector to illuminate a thin glass slab. Due to attenuation, the contaminant generates a shadow map on the Lambertian board, which gives the measurement of the optical thickness. Here are some acquired textures. Image intensity is proportional to the optical thickness. We also measure the scattering parameter g of the phase function. The setup is similar. As the laser beam hits the contaminant, it is scattered towards the Lambertian board and generates a falloff on the board, which is used to estimate the scattering parameter. Here are acquired images for some contaminants. As a simple verification, we also show the image for clean glass in which the scattering is minimal. Here are the estimation results. The red dots are the measurement, and the white curves are the fits. We also developed a simple interactive tool to synthesize contaminant patterns from the measurement. As shown, we first select prototypes from the database. Then we use texture synthesis techniques to generate desired contamination patterns, both for the optical thickness and the scattering parameter. We now show some rendering applications. The first example is a glass sphere covered with a uniform dust layer in complex environment lighting. As the optical thickness tau increases, the sphere becomes more smooth and soft, especially near the contour. Eventually, it becomes an opaque, dusty object. The second example is to render a dirty window of a room. This is the clean window viewed inside the room and outside the room. This is the dirty window viewed inside the room. Notice that against the sky, the contamination pattern looks darker, while against the ground, the pattern looks brighter. This is because the contaminants will both attenuate the light passed through and will also scatter light from other directions from the environment. This is the dirty window viewed outside the room. Here we show the dirty window over the course of a 24-hour day. As the illumination changes, the contaminants generate interesting effects due to the scattering and increase the realism of the rendering. The third example is a monitor with fingerprints and dust. The contaminants are almost invisible to us when the monitor is on, while they are clearly visible when it is off. Moreover, as viewed from more grazing angles, the contamination effects become more dramatic. Both of these effects are consistent with real-world experiences. Our fourth example is a cognac glass covered with a uniform layer of dust. As the dust thickness increases, the body of the cognac glass has a similar appearance as the glass sphere example, while the base of the cognac glass and the caustic show interesting effects as they become dimmer and smoother. Here we show a cognac glass with a textured contaminant, with and without scattering. As the light source is moving, notice the subtle visual effects produced by the scattering, including the vertical shadows on the glass body, the contrast reversals of the contaminant against the background, and the increased scattering at grazing angles. Besides rendering 3D scenes, our model can also be used as an effects filter on 2D photographs to generate contamination appearance. This example shows that our model can be applied to change the photograph as if it were taken through a glass that had been sprayed by seawater. Using a photograph with a clean window, we can generate a new image with a dirty window. Notice the brighter appearance of the window on the bottom right and the darker appearance on the top.